Today we're going to look at the Hiperface Absolute Encoder with SIN cosine. This is a somewhat popular old style feedback device. I think it's from like the 1980s. Anyways, a quick peek at this will show that we have a SIN cosine voltage used differentially to determine the interpolation position over time. The Hiperface Absolute information is too slow to stream continuously at the position loop update rate, so we can get it after power up or reset. They have single and multi-turn absolute encoders. So the SIN cosine comes in, and we do control on that. One of the problems I have with Hiperface is the voltage they say is required, which is 7 to 12 volts. I've got an Allen Bradley here that is a 230 volt winding that has a 5 volt. Okay, so they do make it, they just don't tell people they make it. But a lot of motor manufacturers make drives with 5 volt outputs, like the Copley. So there's data. You know, it's a bi-directional transmission of absolute data. You ask and you get, and so it's like a serial protocol here. So that's the basic Hiperface. Here's an Infranor that has similar things. They talk about the 12 volt on one of their options, SIN cosine, but they also talk about a 5 volt option. So this is a typical option for a drive. There's the current, 300 milliamps. So data and SIN cosine. The motor I have here is a Allen Bradley PM series low inertia motor. It's a multi-turn, 4096 counts per rev. It's a little 230 volt motor, really fast, 8,000 RPM, about an amp of current. Gives us some healthy torque with low inertia. And we can see the cables on there, a motor and feedback cable. I had to dig a little bit, but wasn't hard. So we can see that when we're using the 230 volt motor, we got the 5 volt option. We don't have a 460 volt drive and a 9 volt option yet, but that would be nice to have, is more voltage for longer distances. Anyways, there's the pin out, and you can wire this to the Copley drive. So I've got here a Xenus compact with the Allen Bradley motor power, feedback signals hooked up. That's the Hiperface with SIN cosine. Got this little adapter here that I'm using for the stow. This is something that I think we should stock, so I got to find the price of it. I have a USB to RJ11 adapter, the little Ella Stream Copley USB to RJ11, and this is how I'm connecting to the drive for setup and tuning. I got AC power 120. That's a 230 volt motor, so we're only going to be able to go half of the 8,000 RPM. I got the motor power wires, UVW hooked up, and the 24 volt keep alive. There's a brake option that could wire here if you had a brake. And command and control. This is an EtherCAT drive. We also have a CAN open. So let's take a look at setup and tuning. So the first thing I'm presented here is the basic setup. Initially, we won't find the Hiperface in the CME2 version 7.1 beta. I'm using the 33. So what we have to do is load the latest beta software, CME2 version 7.1. If we connect to the drive, we make sure we have the 5 volt Hiperface and not the 9 volt or 7 to 12 volt. And you use the CME2 Tools login, Copley, CCC. This is breaks into the feature set that we don't market, and you'll get Hiperface in the pull down list. Yeah, this is a 12-bit single turn 4096 multi-turn 128. They call it line. That's a fundamental 512 counts per rev with an 8 times interpolation for 4096. I set this the same as my absolute position on power up, so I don't have to worry about the resolution of absolute position. After I power up, I can move from there, and I know my absolute position. So here's a basic wiring diagram that shows the connection of the data, the sine, and the cosine with respect differentially transmitted. And if you don't have the 5 volt, then you got to power that feedback device with a 9 volt. This is an Allen Bradley defined value here that I got from their 400 volt motor. And of course here you can monitor sine and cosine to make sure you've got that hooked up properly. Make sure you got some plus or minus about 500 millivolts there. So back to the basic setup. Brushless rotary, that's what I got. Hyperface from the list. If you don't see that in the list, again, tools, password, login, Copley, CCC, okay, and then that'll reappear in the list. Hyperface, I'm going to do EtherCAT, COE, that's fine. You can emulate the output. That's not a lot of counts per rev. It's not a high res because it's a really old style encoder, but they do make new ones, so perhaps they'll sell a 5 volt one too. So I got the data put in for this motor, 24 volt KRPM. This inertia came out of their data. It's an 8-pole motor, so I'm not sure if they're all 8 poles, but they probably are. That was easy to determine. There's peak and continuous torque. I put in the max theoretical limit based on my back EMF. I don't have 250 volts, but if I did, I could go that fast, perhaps. Except this is a very large resistance, 46 ohms. So 1 amp times that, that's like 50 volts gone just for delivering the continuous current. 3 times that, and you don't have any more voltage left on 120. So maybe 4,000 RPM is not so bad. High inductance, that's fine. Feedback tab, 12 bits, 4096. Number of revs, same thing, 4096. So I got a 128 line, 512 counts, interpolation 8, gives me 4096 counts per rev. I calculated initial tuning values, and let's hit calculate. So after I calculate, I'll have to remember to save the flash. That's good. So do a little bandwidth check, amplifier disabled. Let's check that out. I got a motor over temp. I don't have a motor temperature sensor, so I'm just going to turn that off. And active low enables. Okay, so now I can do the bandwidth check. So this is bandwidth check based on the calculated values. So I've got gain values of CP and CI. I've got peak and continuous current based on the data I put in. Whether it's amps RMS or amps peak, I'm not sure, but Copley is amps peak. So kilohertz of current loop bandwidth, that's perfect. All that from the motor data. I'm just going to save the flash so I don't lose anything. Confirm the current loop tuning's done. Manual phasing, enable. All right, rotating forward, rotating reverse. Well, a little tweak here and there. I want the black needle and the red needle to overlay. That's pretty good, balanced in both directions. So when I go forward, counts go up. I can do a whole amp, why not? So yeah, that looks more like dead nuts there. Everybody gets a chance for UV and W current as I rotate through the electrical cycles. 8-pole motor has 4 electrical cycles, so you see the motor shaft rotate 1 time with that. So, okay, phasing looks good, and we're going to jump into a little bit of tuning. We'll just check out the current loop tuning. That looks nice, small current. And we can do an amp. So large current, that's fine. Let's check out a little velocity loop tuning. That's some crazy high acceleration, but let's bring the frequency down a little bit. Auto setup checkbox, 3 Hertz, and we should get some nice back and forth banging of the motor. My gains look pretty good here. If I double my gains, eventually I'll break into a point of oscillations. I have a 2-pole filter at the velocity loop, so I'll knock that down. All right, so I got some buzzing there. I'm going to go to a single pole filter. So what the single pole filter does is it improves the phase. So you can see the buzzing. That was a 200 Hertz or less buzzing. Now with the single pole, the buzzing's gone. So give it a little bit of integration there and see if I get some integral wind up. That's pretty good. We might bring the integral down when we do the position loop. So profile, I'm going to do 4096 0. Oh, let's set the auto setup. 4096. Let's look at the current, actual current. Okay. So that's 10 revs at the motor shaft with a safe trajectory. So I should be able to do 4,000 RPM here. And I'm going to increase my acceleration because I don't have a load. See if we get a little more overshoot on that. Yeah, so I got a little integral wind up there after the move, so I'm going to turn the integral back down. Do that again. Because this is a 230 volt motor and I've got 120 volts, I'm going to check my margin. So we'll look at the voltage bus, and voltage terminal servo, and miscellaneous, warning, voltage limited. So when I accelerate, I'm using about 0.4 amps. I can see you're already starting to bump into the voltage limit warning. And give ourselves a little bit of headroom by moving the max speed and bus clamping. This might just give us a tad more voltage to play with. So we turned off circular limiting for smoothness, and we got a little more improvement there. So I'm going to try to go 5,000 RPM. Fingers crossed. Don't think this is going to work. There's a warning. Okay, I got to move this limit out of the way. Let's never exceed 10,000. It says we can't do it with 120 volts. I agree with that. So let's see if we can go too fast here with 120 volts. There you go. Following error fault. So I'm going to clear that fault. Yeah. So at some point, the following error just went to the moon. So let's bring that back down to 5,000. And we'll simulate a bigger load by increasing the acceleration here for current. Still, if you hook up a large inertia, you'll probably want to turn PP gain down, and the VP and VI may actually go up a bit. We made this move, but still voltage limited constantly, following errors going to the moon. Back down to 4,000 with some high acceleration hitting about an amp. So yeah, during acceleration, you get a little blip of a voltage limit. That's fine. Your following air is not growing, so we can bump our heads on it.